not for this audience, but I think that there are some components in there which might be useful for you. So, so I might be able to rush through this a little bit. It relates a little, somewhat to my new job, which is at the Fraunhofer Project Center at the University of Twente. And in additive manufacturing, what we are finding, I think I've mentioned it to a few of you already, is that there is this, this shift in the technology at the high end. Okay, so some of you are familiar with some of the metal printers, some of the larger polymer printers. If you think about all of those printers, how many of them would actually be able to be put onto a factory shop floor and would survive? Not many, probably not any. All the machines I'm sure that you're running are sitting in a laboratory with reasonably good conditions, probably air conditioning in order to make sure that you don't get too much humidity, you've got powders which clump together if you've got humidity. You have to store your powders in careful environments, otherwise they go off. They may oxidize and similar problems. Polymer powders and polymer materials. Who prints with PLA? Yeah, a few of you. So if you unpack a PLA spool, how long does it last if you just left it out? Huh? I mean, I used to run PLA on some machines, and I used couple of times I've just sort of left the spool on the machine, and maybe 2 or 3 days later feeds through it and it starts to break. It's already degrading. Yeah. So all of these things are undesirable for continuous industrial production. So we have to think a little bit about that. So I made this presentation to try and convince people that there are changes on the way and that we need to be part of this. So this is a different slide. I've not mentioned this one before. I have a few which I'll just skip through. But the thing about 3D printing, it's changing the world of manufacture because it can be applied in many different ways, many incarnations. As I mentioned to you already a couple of times, industry has always been interested in 3D printing because they realize the benefits. They may not think that the machines are currently able to achieve those benefits, but they can see how it may do that in the future. But even so, some machines, they're already saying, yeah, even 20, 25 years ago, they were already saying it was useful. I remember talking to one of the first users of a stereolithography machine. He was a chief engineer at Ford Motor in America. Okay? And he said that he ran the first project that he ran on his machine, the first serious one, after doing all the validations and the training. He ran one project. What did he do? He worked with the purchasing office for Ford. And the purchasing office, what do they normally do when they are wanting to make a part or have a part made, third party? They have a drawing set. They send the drawings out to a number of companies and get a quotation from the companies. Okay, so they ran a test. One, they sent to 3 companies with just the drawings. One, they sent the same drawings but then also a 3D printed example of the part that they were going to make, that they wanted making. Every single quotation that came back from the companies that got the part quoted lower than those that didn't have the part. Because basically they said, there may be, we do this, but we look at the drawings, there may be some things on the drawings that we don't quite understand. They put a contingency markup on the quotation. So imagine if you're a company like Ford, and we're talking maybe a door handle or something like that, and your quotation is 10 cents lower than the other quotation. How much are you going to save? They could save hundreds of thousands of dollars, and this is what this guy calculated. He saved enough money on that one project to buy the machine. Okay, so industry has always understood the benefits of additive manufacturing. What they don't understand is how it might benefit them. Okay, some of them do, but a lot of them don't. Okay, it's evolving. We buy a machine this year, next year it's out of date. How do you justify buying a machine? Okay, just to put something in context here. Okay, anybody in this room does not have a mobile phone? Good, right? So everybody has a mobile phone. How many people bought their mobile phone in the last 12 months? Not many. I don't believe you. You sure? So only about 20% of all the people in this room bought a new mobile phone in the last 12 months. You sure? Okay. All right. So who said who put their hand up? Okay. When you bought your new mobile phone, what was wrong with the old one? Okay. All right. So you replaced it. Okay. You had a really old phone and you replaced it with a good one. Okay. Who else? How about you? Same? More RAM. Okay. Now we're getting there. That's most people's reason. Okay. Usually the reason for buying a mobile phone is not because the old mobile phone didn't work. Correct? It's because you want bigger screens, more memory, faster Wi-Fi, blah, blah, blah. Yeah? So I just sort of want to make a point here, is that, you know, these days we're in a consumer society, and when we want to buy new stuff, it's usually because it's our head telling, our heart telling that's not our head. I suppose what I'm also saying is that, you know, we're relating to additive manufacturing, you have to make the justification at the time. That's kind of what I'm meaning. You just basically say, okay, it's time for me to buy a new machine. Why? Because, and if you do it, you must make a business case for it. So it's quite important to understand that, okay? That it's a very fast-moving technology, and therefore, you know, okay, I'll wait till next year. Next year comes, oh, there's another machine which is being announced that will come in 6 months. I'll wait till that comes. That machine's delayed. Yeah. So when do you actually buy your machine? So you have to make your business case based on what is the current situation, not what is the situation in the future. But then when you buy it for one purpose, and very often you find that you're using it for another purpose and another purpose and another purpose. I once talked to a company. They asked me to sent me a picture. Said it was off a printer. This was a company that was food packaging, chickens, and they print labels to go on the packages. So they had a printer, industrial printer, and they printed it. And they kept finding that they have maybe 50 of these printers in the factory. And this door on the printer kept breaking. And said every time we asked the company to replace this door, they charge us $30 for the door and $50 for replacing it. So, this is expensive. Can we do it? It just looks like a simple piece of plastic. I said, yeah, no problem. I said, will you print it for us? I said, no. And I said, why don't you print it for us? I said, well, why don't you print your own? We don't have a printer. Why don't you have your own printer? You've just told me that if you printed 3 of these doors, you could save the money to buy a printer. He said, but we only need to replace them every 3 months or so. I only need to maybe do 3 a year. Well, yeah, you've saved your money on your machine in 1 year. That's a great ROI. He says, but it'll only take me half an hour or so. So what do I use with the other? There's your question. What do I use the printer for as well as printing the doors? He said, look, then that's where you get your benefit. Because you can use it for another thing and another thing and another thing and make a lot of money from it. Okay, so I think I got a bit on business. I'm maybe talking too much about business today. Don't ignore the program, by the way. We'll cover most of the stuff, just not in the right order. Okay. And I mentioned about technology convergence. I got a slide on that. All right. What do I mean by the different incarnations of 3D printing? I mentioned that rapid prototyping was what it used to be called. Why was it called rapid prototyping? Because that's what we used it for, making prototypes rapidly. At the time, we are talking in the late 80s, early 90s, when companies didn't have CAD technology, never mind laptops and stuff like that. Didn't have, a computer was a huge thing and a huge investment and required a lot of skill and training to have. Okay, but then companies were starting to introduce 3D solid modeling CAD. They started to get all that coming in, and then there was this. Then they realized that how long did it take to make a prototype of a new product? Not only did it take a long time, it cost a lot of money because it was a very skilled task. Because we were talking mainly dealing with sculptors, artists, making these prototypes. And you want to make a prototype of a door handle, and make sure that it actually works. If it's on a car, it's got to work, it's got to be tested, it's got to be validated. How do you go through that process? It takes months. Because every time you make a part, make a prototype, it maybe cost you $1,000 just for a prototype door handle. And then what do you want to do? Test it till it's broken. So how many do you need? So there's a lot of issues there. So prototyping was what we were doing all of this for, to make prototypes. Never thought about actual manufacture, not really. But then they thought, well, okay, it would be nice if I could make more than one of these things. Now, nowadays, we think, we'll just print more. Because, you know, somebody told me he's making a medical, you tell me, you make your medical models, and it costs you $50. And that's a retail cost, I imagine, okay? So if you had your own machine, it would probably cost you $5, yeah? So now, it's, rapid tooling doesn't quite make the sense that it did then. Because if I want to make one part, I use it as a pattern to make 20 parts using silicon rubber molding. That's good investment. Saves me the time because it was a slow process then. Saves me the cost of making of resin and stuff like that. Okay? So rapid tooling kind of went out of business for quite a long time. Interestingly enough, it's coming back in again, but for different reasons. This is where a lot of stuff is going on now. This is where a lot of activity in industry is basically saying, forget about tooling, let's just make the parts. And somebody was asking me about, yesterday I think it was, about volume. What, you know, if I want to make 100,000 parts, does it make sense to use 3D printing or not? Quite often now, yes it does, for a number of reasons. One is that once your part is designed, you can print it. So turnaround time from design to part, art to part, is significantly reduced. You don't have to go through any cost and time and effort in building tooling. Okay, so you're fast. You now have machines which print fast, like the HP machine. So you can make lots of these parts relatively quickly, and you can stack them, and there's lots of software to help you do all your process planning and making sure that it's all properly distributed and it's all automated. Okay, you can also, the cost of the machines have come down, the costs of the materials have come down, so the equation keeps changing in terms of what is the break-even point on volume. Okay, so it's an interesting dilemma now for a lot of manufacturers to whether they even bother to go to tooling. If you're making millions of parts, still it makes sense. You're making lots of parts which are very simple geometries, still it makes sense to do traditional. But if the more complicated they are, the lower volume you need, which is the world that we live in. As I said, mobile phones, even mobile phone volumes are coming down because they're shortening the time to the next iteration and the next iteration. Okay, so there'll be a point even when maybe even mobile phone casings will be 3D printed. It's a little way off yet because of the material properties in particular, but it's not impossible. 3D printing is all about the low-end stuff, all about the innovation stuff, which I was mentioning before. There is also a growth area here. People saying, where should I be looking at my research? Somebody was asking me about hybrid manufacturing using powder bed systems. Is it done? Yes, it is. It's a limitation because you have to machine your substrate to a single precise layer in order to do it. And yes, there are some issues, particularly in relation to bonding of the part, the printed part onto the substrate, but it is being done. Okay? Direct energy deposition, the lens process, that was one of the things that they were saying that's what their machine is best for compared to powder bed systems. That's not really true. It may be a little bit more versatile, but not necessarily correct that it's better than a powder bed system. So these are things to consider. So there's a lot of work on hybrid. Hybrid means additive and subtractive. Adding material and then using another mechanism to machine away in order to give you better precision. Okay? And if you can do that in process, then it's beneficial in a number of ways. You know, you can control the process a little better. You can get better, more accurate output. You have benefits from not having to program your machining G-code so precisely. Mass customization, we're starting to talk about. We've mentioned a few times about basically taking data from people and incorporating that into the manufacturing process. So having the customer drive the manufacturing process to a certain extent. Have you ever heard of the term prosumer? Yeah? So as an alternative to consumer, pros and cons, okay? So a prosumer is essentially an active consumer, somebody that is involved in the process of creating the parts that they're going to use. And that really, it sort of relates very much to mass customization or personalization of parts. And then bioprinting, and there are others, stuff that's not on that list as well. Okay, so don't really need to know about that. We've seen plenty of printers. High-end printers. The one I'd like you to focus on is actually this guy here. So this distance from here to here is 11 meters. That's a 3D printer. Okay, it doesn't make parts 11 meters long. Okay, it's a modular system. This is the Metal Fab 1 from Additive Industries. It's about 100 kilometers away from where I live. And we're working with those to get one of their machines. What do you see about this machine? You see it's got these modules. So these two modules here are both build chambers. So it's got interchangeable build chambers. Okay. A lot of you are talking about using metal printers and wanting to do cobalt chrome or maybe titanium or maybe stainless steel, as if it's quite an easy process to switch from one material to the other. It's not. Okay? And particularly if you're moving to titanium, if you've been running another material prior to that, the chances of contamination effects on the build can be extremely high, particularly on the first builds. If you've ever seen a machine and ever worked with a machine and ever tried to clean the powders out, it's not an easy process. And partly because it's a lab machine. This is what I mean. So what alternative ways are there to deal with it? One might be to redesign the machine so that it is actually very easy to clean out, which some people are doing, but it's a tough job, and you still have to do quite a lot of manual intervention to do the cleaning. Another, multiple chambers. One chamber for one material, one chamber for another material. See this module on the top? It moves backwards and forwards. That's the laser system. So what you do is you have the laser on one side, on one machine, so you switch that laser down there, it does the build. On the other side is the part that's already been built. Takes time to cool down or heat up. So the switchover time is actually quite good. So the downtime on the machine is minimized. Certainly laser time, or we call beam time. So when it's building on one side, you're dealing with the part on the other side. And yes, it takes a long time to heat it up, a long time to cool it down. So there's not that much difference in the timing between build and pre and post build. So your downtime is very short. At the back of this machine is a robot. There's a robot which basically picks the part out of the build chamber, puts it into another module where the powder is then shaken off the part and recycled back into the powder feed system, if that's a way to do it. Some companies, they don't want to do that. So it has an internal powder handling system, an internal sifting system. Anybody actually operate their metal printers? Yeah, a few of you. So you know what I'm talking about. How much time it takes to do the powder handling, the sifting, how much time it takes to make sure that it's all set up, the heat up, the cool down time. Yeah? All problematic, all time consuming. A lot of that is now done inside the machine. There's another chamber in here, has a heat treatment furnace. Okay, a lot of builds. I mentioned about support structures. Metal printers build in a powder bed system. I told you that for the SLS machines, for the polymer, you don't need supports. When you build them with metal, you need supports. Why? Yeah. Sorry? Yeah. So it's about thermal gradients. Basically, what do you melt titanium at? Was it about 2200 Celsius, something like that? Is it? Can't remember the exact, but it's hot. Okay. You remember I mentioned about the polymer system. You heat the powder up to just below the melt point, and then you use a laser to melt the powder. Don't do that in a metal machine. You don't raise the entire temperature of the powder bed up to 2000 degrees and then just melt the rest of it. That's not very practical, and it doesn't work anyway. You get sintering effects and stuff. So you heat the powder up. Its surrounding temperature might be only a couple of hundred degrees, and yet you're melting it at a couple of thousand degrees. So when it cools down again, material shrinks, and it cools down very quickly. And if you don't fasten it to the base, then it'll go as it cools down, as the thermal gradients, sort of uneven gradients, take charge, and your internal stresses take charge, and yeah, you get rubbish. So it's important to have support structures. So you put your furnace, you have a heat treatment furnace, basically is usually quite important, because even if you took the part off the part bed, it's still possible that it may distort and crack and things. So heating it whilst it's still on the bed and controlling the temperature over time is a useful process. There's another unit in there which slices the part off the platform, and another unit which stores the platform. So that is what I mean by industrial 3D printing. Okay? And you could buy just, one control unit, one powder bed, and one laser, and you've got the minimum machine, or you can extend it to one of these. Okay? So that's their philosophy. I mentioned about hybrid machines. This is a hybrid machine. So this is a laser additive process here, adding to the part, machine tool, machining away the surfaces. So combine the two together in some kind of sequence, helps you to machine internal surfaces and make sure they're precise. If you 3D print an internal surface, how do you finish the quality of that internal surface? So think about your bone implants. You're using some kind of hollow mesh. What's in the inside of that mesh? Now, sometimes we talk about that. That's a beneficial thing because rough surfaces are quite nice for bodies because the cells like to attach themselves, but not necessarily. Okay? And you might also say cells can attach there, but also viruses and other undesirable bacteria can also attach themselves in there. So sometimes you don't want rough surfaces, internal surfaces. How do you deal with it? Not easy. Okay, let me forget about that one. I won't deal with that one. This is an interesting one. This is a 3D printed part. There's a laboratory in the US, the Lawrence Livermore Laboratory. Some of you have mentioned it. They said the BAM technology, Big Area Additive Manufacturing, they call it BAM. Maybe not that relevant in the medical context, but it's interesting, I think, anyway. This look, do you see the shape of it? What's it look like? Sorry? Windmill blade, absolutely. It's a tool for a windmill blade. They make them using carbon composites. And this can be, for some windmills, can be 30 meters long. Some of these windmills are huge, absolutely huge, scary things. If you're using composites, carbon composite manufacture, it's exothermic reaction, yes? Exothermic process. So if you've got a tool this long, you start putting your carbon layups here. By the time you get to here, there's all sorts of distortion going on here because of the reaction. So you need to control the heating and cooling processes. And what they normally do is they put copper wire into the surface of the tool. And that copper wire, then they control the temperature. So they keep everything at one temperature, everything's laid up, then they gradually cool it uniformly. Okay? In order to make a tool this size, you need something like 150 miles of copper wire. Okay? So, and it's all laid by hand. So it's expensive, difficult, time-consuming. So somebody took the idea of making these tools and making them hollow. So you can see inside there's cavities in here. So what they do with this tool, instead of all the copper wire, they just blow hot air. So they have different chambers, and they blow hot air into each of the chambers. And therefore they gradually control the temperature of the air in each of the chambers, and therefore control the cooling, heating and cooling of the tool. I just thought it was interesting. These are just all the machines that they use. So it's a big lab, but it's interesting. I think there's a lot of work on big parts now. It's basically, so this is the printer. So they've experimented with both, but in fact, the printer moves. So they basically just have a huge frame, XYZ, and they print from there. So it's just huge. But if you look at this, you probably think that it would be best to build it that way rather than that way. And I agree. So probably what they did is they actually build it in segments and then join the segments together. For something like this, there's still quite a lot of manual intervention at the moment. But a smaller version was made to build car bodies. There's a car that was called the Stradi, a company called Local Motors in the US. And they demonstrated how you could build an electric car in 2 days. And they did it at a car show, I think the Detroit car show, something like that. Basically, they took the machine to the car show, they printed it, they put the wheels, the drive system, so it's an electric car. I think altogether about 40 components. A normal car is what, 10,000, something like that. So this is like, okay, they have a control board, a motor, driver, steering system, bit of suspension, wheels, 40 components. It was a bit of a showpiece, and it's not a roadworthy, well, it is a roadworthy vehicle in America, actually. I'm not sure it's a very roadworthy vehicle for India. It was a bit small. But they demonstrated it, and now there is the Stradi 2, which is used to build cars, which you will find on some of the airports in America, because they're used as courtesy cars and buggies for taking stuff around airports. And so basically, in a controlled environment like that, you've got this car. If you look it up, Stradi, S-T-R-A-D-I, Local Motors, you'll see how it was done. And then you look at the Stradi 2, which is a bit nicer, a bit prettier, but does pretty much the same thing. Sorry, say again? You mean the fittings? Sorry, I'm going to have to come closer. I'm not quite understanding what your question.
Just like it is an FDM machine.
Yes.
So in an FDM machine, we are using the 18-cubic nozzle.
Yes.
For that.
Yes.
So commonly for 500 cubic machine, we have a dual.
Yeah. Okay, got you.
So the nozzle arrangement.
Yeah, this is, as far as I know, it's a single nozzle, but it's a very big nozzle. So it's probably about 1 cm diameter. Yeah. So what it's doing is building very thick layers. If you look at you can even see it on here, at the body top here. You can see a bit of texturing here. That's the layer thicknesses there. So the thicknesses are very thick. So the expectation is that you do body filling or sanding, normal sort of workshop type activities when you're doing car bodies. It's a carbon-filled material, and so the idea is that you want to build it quickly, and then there's a trade-off between the build time and the post-processing time. So it's the same with these guys. You can adjust it, you can have different nozzles on there, and this was something else that somebody was asking me about, which is something that some researchers have dealt with. Big nozzles, small nozzles, on the same machine. So you can do outlining of the part using a small, thin nozzle. Get nice, precise outlining. What about the infill? Now, a lot of people, they use lattice infill. Part of the reason for lattice infill, well, there's two main reasons. One is speed, but the other one is you get actually better precision on your build, because you don't get so much heat in the build. But sometimes you need a solid. So when you need a solid, what do? You have to infill with a solid fill. That's time consuming. So why not have a big nozzle? So build three layers. Big nozzle fills in 3 layers. So you can have a nozzle 3 times the size, doing a lot of the infill stuff in 1/3 of the time. So what they call big area, fine detail. And these guys have been doing some stuff on that as well. So in essence, what you're saying is absolutely a valid question. And a lot of people would therefore not use that technology for that purpose. Now, this is when I start making my translation from additive, from 3D printers to additive manufacturing. This is more on additive manufacturing because I could quite easily have like a Dremel head or something like that on as a replaceable head to the nozzle. So I extrude, I then finish, and then go back to extruding again, like the Morisaki machine. And I could do that, but then it becomes hybrid. It becomes, is it really a 3D printer? Do I care that it's a 3D printer or what it's called? Because it's doing the job that I want it to do. And you could think about that from production perspective. And you think about, and I've got a great example, and I'll show you in a couple of slides of what I mean by that. So this is a prototype process to demonstrate the process, but when you get to this stage and you're building prototypes, you're pretty close to manufacturing because this is a big investment. It's really just to say, okay, this is where the future is and one of the possibilities and why. So they're really doing a bit of a justification exercise here rather than necessarily it's a fully commercial process. But the lessons learned for doing stuff like that allow them to do projects like that. And that, the first one off, was a test. The second one, commercial. And they're already making lots of money from it. That is applications research. Okay, this slide I've already covered. I'll not be too much about this. Although this is a really good example. This is one of the aerospace examples that I use. It's quite famous. How many people have heard of the GE LEAP engine nozzle? Quite a few of you, but not everybody. This is a commercial product. Okay, General Electric make these and put them on their engines. So chances are that you may, even if you flied in the last 2 years, may even have flown on an aircraft with one of these on. Okay? So which means that it's been validated to aerospace standards. So it is not a prototyping process. Why are GE interested to do this? For these kinds of reasons. All right? It's got internal features which are difficult to fabricate using conventional manufacturing. The only way to fabricate them is to fabricate them in pieces and then assemble the pieces together. In an assembly, where is the weakest point? At the joints, at the interfaces. So if you make a part that used to be 19 parts and is now 1 part, it's actually significantly more reliable. The reliability increases immensely. Okay, it still joins. You know, you've still got connectors here, you've got connection points here, you've got a connector up here. But it still reduces the overall number of components. When I mentioned about the Stradi, down to 40 components, that's because the entire body and subframe and everything was built as a single piece. In a normal vehicle, you cannot do that. Right? So a lot of this is about saving on parts, improving reliability, making it quicker and easier. In aerospace, they're constantly going about weight saving. You know, 1 kilogram saving of weight on an aircraft, on a passenger aircraft, is enough to save you, I think, about 100,000 US dollars in fuel per year. It's a big issue, yeah? That's why they keep weighing your luggage. Well, that's what I mean. It's combined. So maintenance is reduced. The amount of maintenance is reduced. And the replacement process is simplified because you just take one of these off and put on another one. Yeah? Now, all of this sounds great, yeah? And it is. But one of the things that you then have to realize is GE, to get to this stage, it took them 15 years. Now, it won't take them 15 years to get the next part. A lot of that is learning the ropes, learning the processes, understanding the machines, influencing the design of new machines so that it works the way they want it to work. That's why GE bought Arcam and Concept Laser, because they wanted to control the manufacture of the machines and understand that, so that their the parts that come off it are to their standard. And the same would apply to the medical industry. Absolutely, 100%. So this is the kind of areas we're working in. The point here is that this is a message that has to go then to your Tata Steels or whatever, you know, your Fords and things like that. This is why they bought the machines in sort of the 90s rather than just buying them today. And what we're now saying, we're having discussions with lots of companies that we're just waiting. And now I think, 3D printing, I better get involved in that. Maybe I should buy a machine. Okay, what machine should I buy? Well, that's not the first question you should be asking. Because the first question you should be asking is, what part am I going to make? And how am I going to make it? And why do I want it to be made in that way? So there's nothing in this about customization. So GE have printers in their workshops that are only printing one type of part. So we talk about 3D printing as being, oh yeah, we can do switching of the parts. As soon as your design is modified, you can then switch it onto the new design. You can customize parts. All of that is true, but not essential for a business case. Okay? Right. Let's go on to medical, just before lunch. Here's a good one. So this is just a nice example from a good friend of mine who is based in the Netherlands. His name is Jules Pookins. And he is one of the chief surgeons that works with Materialize. And he has loads of cases like this, where he's doing essentially a big cosmetic surgery. If this guy walked down the street of Warangal, you probably be a bit taken aback, yeah? So we're talking about giving people their self-esteem, self-respect, by making 3D printed parts of this kind of way. And it's similar to the ear thing that I showed you before. That's that one, the lady was able to, you know, she grew her hair long, and so people wouldn't really know that she didn't have an ear. This one, that's not so easy. You'd have to have a big face plate like Phantom of the Opera guy, you know? So somebody asked me about the molding process. You remember in the video that the guy made the ear on the 3D printer, but that 3D printed ear didn't go directly onto the patient. Why? So there's a couple of reasons why. One is the validation processes, which we keep talking about. currently that process is not allowed, even if the materials were acceptable. There is no protocol for doing it that way. Okay, there's nothing wrong, however, in the person making the ear to choose whatever tools he or she likes to make the ear, so long as the material and the overall process is not compromised. So the normal practice that the guy at the Royal Melbourne Hospital did was he would actually carve an ear. So he would be a sculptor. So he'd take lots of measurements and then take those measurements and then gradually, through experience, carve an ear. And then he would use that ear as the mold, to create the mold using silicon rubber molding. So he'd use that ear as a pattern, cast a mold around it, and then into that mold he would then pour silicon rubber, another silicon resin, which he would be very carefully coloring to make sure it's skin colored. And then he'd take that out, and then at the same time, or rather, he would insert the magnets, trim it all up, fit it onto the patient, do the final cosmetic adjustments. So you remember him saying about all the accuracies, that's why he liked it. This is why. Because no matter how good a sculptor he is, he's not going to match exactly the other ear. He's going to have some problems with, some making blemishes and other things onto that part. All of these things can be gone because what we've done is scanned her good ear and then just mirror imaged it so that it fits on the other side. And this is the same sort of thing that this guy, that Jules does here. So you can see he's scanned his face on this side, and we've created another mold on this side. Notice that the coloring's not precise. Well, it's not going to, is it? Because you've got blood vessels in your face. You know, if it's hot, your face goes red, or at least mine does. Okay, and if it cools down, it goes paler. So you're never going to get it unless you can have some kind of, I don't know, photoreactive paint on the top of it that reacts the same way as skin does. So it's never going to be perfect, but it should be good enough to allow him to just walk down the street without being looked at. So it's really just aesthetics, it's not anything else. Okay, I have a question for you, which you probably already know, because it's a bit obvious. So we've got aerospace, automotive, and medical as the three primary industry drivers for additive manufacturing. How many think that aerospace is the most profitable? 1, 2. How many people think automotive is the most profitable? A few more, half a dozen. How many people think medical is the most profitable? Okay. Yes. From an additive manufacturing perspective, medical is definitely the most profitable sector. Ravi mentioned that it's not necessarily where most of the parts are made. So more parts and more money is spent in aerospace and automotive, but more profit is made in medical. And in fact, in one particular sector of medical, which is dental. And in fact, there is one company that stands out amongst all of this. Anybody want to tell me the name of the company? Huh? Who said Stryker? No. Align Technologies. Invisalign. Anybody heard of it? Yeah, a few of you. Just about see it. See, the lady in the back is wearing steel braces. And those are wires which help to do dental alignment. This lady at the front is also wearing braces. Just about see. It's a clear plastic brace. How does it work? Well, what you do is you do a scan of the teeth. You take that scan and create a series of aligners, these plastic aligners. Each of these aligners are a graduation from the current tooth alignment to the final tooth alignment. So you got a graduation. So you could have up to 20 or 30 of these aligners that you put in for a week, take one out, and then put the next one in. And gradually your teeth get pushed into the correct locations. They're kind of like gum shields that you use in in sports, but they're obviously clear, very thin plastic, and they're placed. They work for a lot of cases, not for every case, and Invisalign is now trying to come up with systems which address some of the more severe misalignment cases as well. But it's a very interesting company, and this is their factory. And I have no idea where the 3D printers are. It's in there somewhere. There's a few of them, and they're in there. Now I want to show you a video of the align process. Okay. What's happened to the volume again? Hang on, let me see if I can... because I turned it off.
Align technology has played a key role in the evolution of orthodontic treatment. In the early days, we were viewed as a technology and market disruptor, and we still are. Today, we're the leader in clear aligner orthodontics and an emerging leader in digital dentistry. We believe our products can and will be part of almost every aspect of dental and orthodontic treatment. To do that, we have to provide our customers and their patients with the very best products possible. We constantly invent and then innovate to bring the right products and features to our customers. We combine the knowledge from millions of cases with 3D software engineering, material science, cutting-edge manufacturing to help doctors deliver treatment that is more predictable and more efficient than ever before. Our market share is still small. Many treatments are still done the old analog way with brackets and wires and physical impressions, but we're changing that. Our goal is to ensure we can do anything wires and brackets can do, better and more efficiently, and deliver a great experience for doctors and patients while doing it.
Invisalign is more than capable of keeping up the pace of innovation. What pushes the innovation is our desire to put the right tools in the doctor's hands to make every case an Invisalign case. Digital treatment planning, 3D tools. Invisalign will become more and more intuitive for the doctors. Digital technologies like scanning are making doctor and patient experience a lot better. For one, it's a lot easier to take a digital impression of the patient than it is to take a physical impression. The more accurate the data, the better your treatment outcome is going to be. We work very hard on our software tools and algorithms to generate as accurate a tooth shape as possible because it results in a better aligner fit. Every single aligner is unique. Everyone is different. It's easy to make a few aligners a day, but it's extremely hard to make tens of thousands of aligners a day with high quality, high consistency, and no opportunity for error. All the manufacturing process and the tools that go behind the scenes to make that happen, I consider to be a crown jewel for Invisalign.
We are probably the world's best at mass customization. It's a highly complex integration of data throughout the world that has to be linked and moves seamlessly amongst all of our constituents and facilities. It starts at the doctor's office with a physical impression or a digital scan to create a 3D model. Then that data is transferred to our dental technicians who use proprietary software to create a digital treatment plan. The proposed plan is sent back to the doctor for review and approval. The approved data then moves to our automated plant where each individual aligner is custom fabricated. Up to 80,000 aligners are made, tracked, and shipped each day directly to the doctor's office. The entire process, regardless of where it's located, is one continuous process flow, and the more we're able to use digital electronic data, the more seamless it becomes.
The Invisalign brand is one of the greatest things about this company. This may be the only product in orthodontics or dentistry that people ask for by name. Our consumer marketing programs directly benefit our customers.
But there's a few things to recall on it. You were about to say something? Correct. Why?
The need doesn't make the necessity for bringing the 3D printer into picture, except the mold or something like the sample molding, and the post-process and the high-scale industrialization also is done with another process other than the 3D print.
Okay. Partly that, but the main thing is that there is actually no current 3D printed material that is validated for constant contact with the body, and particularly internal. So you cannot put any 3D printed piece in your mouth and leave it there. As a company, so that's one reason. Another reason, if you actually look at the thickness of the aligners, they're very narrow, very thin. So they're polycarbonate, I think. There's some form of polycarbonate, clear medical grade material formed using vacuum molding. So the molds are use a 3D printer. Okay, so you got the point there. Yeah, you're right. It's when you think about it as part of a process, then you choose the best processes for the best result. So the shape is extremely important. You've seen it. They've got software, their own scanners, their own software for predicting and designing each of the molds. Something to also mention, when you go into the molding, the data that comes from the dental surgeon or the orthodontist is, it then has to be manipulated by, as you saw, that big, looked to be a couple of hundred people just doing the design. And each of those people are supposed to do a design one design in the space of about 20 minutes. So there's a lot of automation in the software as well. And all of that then goes into the process, so all of those alignments. Logistics. You don't want to be making a dental aligner for one person and sending it to somebody else. Okay, you've got to keep track of everything in your process. So supply chain management and logistics are extremely important. Relay that to putting so they laser etch each of the aligners with a patient code. And so that's part of the process. There's robotics in there, manipulating each of the samples. One of them was, I think, what we saw was sterilization, I think, UV sterilizing the part before it goes into packaging. There's also a robot which is used to cut the aligners away from the panel that it's formed on. So there's a lot of different steps in that process. And they are making, he said, tens of thousands. I think I saw somewhere they're currently on something like 25,000 aligners per day. So, yeah, it's a great business because they're not cheap, but also it's mass production, mass customization in a real sense. And the guy is perfectly right. They are probably the world leaders in mass customization at the moment. There are other companies, but probably they maybe qualify it by saying they are the world leaders in mass customization using additive manufacturing. Almost certainly. Almost certainly. The other companies that are doing mass customization are companies like Mercedes-Benz and the high-end vehicle producers, where customization is where you choose the color of your car, what type of seats, what type of steering wheel, all of those kinds of things. Okay, so that's still mass customization, but it's not personalization. And that's what the Invisalign process is. Sorry, there's a, yes? Sorry, say? You've got a question in metal additive manufacturing. Is it related to Invisalign? No. And the previous slide, okay. Yes, go. Yes.
So, in what way that it affects the part which is being printed on the surface, like if I am printing the
Yeah.
on the surface?
You'll get potential weaknesses in the part. So, no way, if you talk to any of the guys, will you be doing one day titanium, another day stainless steel, and another day cobalt chrome, unless you happen to have a guy that is sort of like working 3 times faster than anybody else, and you know, a machine that's very, very easy to clean. Actually takes almost a day to switch over. Well, more than a day, quite often, to switch over from one material to another. Okay, so that's one point. If you have contamination, then yes, the most likely thing that you'll see is some weaknesses in the part. And they could be quite significant weaknesses. They could result in fracture surfaces. They could result in poor fusion at the site, because what you've got is a material which is melting at a different temperature, contaminating the material. So you then end up with unsintered material, so you get a void. That void can then turn into cracks. In the case of DED, when you're switching from one material to another, you're probably doing it in order to contaminate. In fact, so what you're very often doing is making multiple material parts, or at least trying to. This is not necessarily a bad thing, I'm saying. Powder bed fusion, you are assuming that you want one material, and you need one material. In DED, you may be assuming that you want more than one material. But if you do only want one material, there's still some issues, but because things like, I mean, the optics get affected, you know, and things like that. You get powder goes all over the place. So it's quite difficult to control it all and clean it all out. However, it is still feasible. So I think what you're saying is DED is less prone to contamination, and I would agree with you. Yes, it is. One more question. Say again. I didn't catch all that.
Print the part with DM.
Yes.
The surfaces will be somewhat
Yes.
DMT Mori machine you have shown.
Yes.
In that you have it's a hybrid machine. You
Yes.
have done some post processing.
Yes.
So what are the instead of machining, what are the other techniques are there in which
Ah.
the surfaces can be improved?
Yeah. Oh, sorry. Yeah. So what other ways can you post-process metal parts other than by machining? Is what you're asking. And there are a number. I mean, shot peening methods, sort of abrasive finishing, using ceramic bead tumbling, those kinds of things. We've been experimenting with that in my group for quite a while. There's a nice, quite an interesting one which was developed in Japan called Slurry Finishing, which is quite good if you've got a channel and you want to clean out the channel. So what you have is a very high viscosity fluid which is carrying ceramic particles, and you basically just pump it through the channel, and as it pumps through the channel it abrasively finishes the inside. So there are a number of possible ways to do this. All of them have their advantages and disadvantages.
You talk about the slurry. Is it an abrasive slurry?
Abrasive slurry, yes.
What kind of abrasives can you use for this?
What kind of abrasives? Hard ones.
Yes, sir. But for certain materials, is it affect or something like that?
Yeah, I mean, obviously the harder the particles, the more abrasion you're going to get, the less control over it you have. So it's a time-related function. So you finer particles, softer particles are going to take longer with the finishing processes. So it's a balance. You're looking for a research topic? Go ahead. You said one more question 3 questions ago. Go on, last question. Not one more question, last question. Yeah, it's a problem. That's what I said. There are advantages and disadvantages. So if you've got sharp edges and you want to retain the sharp edges, you've got a problem. So you can do post-compensation, or pre-compensation rather. So make your edges thicker so that when you finish them off. But then the good thing about sharp edges is that quite often they can be machined. So your choice is process dependent. And there's not always an answer to your question. Now you see why my computer's shut down. Okay? But you know, there is always going to be a problem. Okay? It's something I seem to find a lot with Indian students. They love to talk about problems as if that's a way to not do something. Okay? Talk about challenges. Okay? So the challenge is that you've got a external sharp corner. How do I deal with it? Yeah? Not the problem is. They all can be problems, but they basically are solvable problems, mostly. If they're not solvable problems, or you don't think they're solvable problems, that's a great research topic. Okay? There may be problems that can't be solved, but there are no challenges that can't be addressed. Okay? Okay. Anyway, sorry. Apologies for being critical. Now for some reason my computer keeps shutting down. So you have to wait a minute then. You can blame our gentleman over there. It's okay. Make him stand at the end of the lunch queue. Sorry, I'm okay. I'm just playing with you. Just give me a couple of minutes to reboot. It's not that. This one's my computer. It basically, for some reason, sometimes when it goes to sleep, I cannot waken it up. It's kind of like my son. I have the only thing I can do is hard shut it down and reboot it. Yeah, I don't understand. I mean, it doesn't seem to do anything wrong to the computer. The computer recovers fine, but it just takes time. There we go. Right. Yeah. Generic problems. See whether there's any more I need to go, actually. Ah, right. Anybody come across this case on the right-hand side?
So this.
Oh, it's me again. Sorry. I'm answering myself. Oh, yeah. Okay, stop. So this guy, I think he's Canadian high school student. And he read about Invisalign. And he was a bright guy, smart guy. Thought, well, I can do this on my own printer. And he did. And it worked. This is like the before. He's actually got one of the guides on here. This is him after. Handsome guy. More chance to get a nice girlfriend. I don't know. But, so the point here, the reason I put this on is because you've got to be careful. I mean, okay, this is, you know, in some ways you can look at it and say, this is amazing, fantastic, you can do this yourself. And you see a load of these. There's a lot of these around. You know, people that have lost their arm, a hand or something, you know, diabetes sufferers lose a limb, kids in Africa, you know, they lose their limbs for various reasons, skin diseases, etc. I've seen loads of them, and you know, there's any number of these, and there's even there's a great story of a guy in the UK, in Wales, in the UK, that's made like 100 or 200 of these false limbs for kids in the region, and he just does them on his own printer, and it's fantastic. But my concern is that neither of these guys have got a medical qualification. That neither of these guys are, you know, none of these processes have been regulated in any way. So, you know, you're serving a real purpose here. I don't want people to stop doing it necessarily, but you have to be careful. I particularly refer to like this one here. Now, what if, and it's not that 100 miles away from the case I mentioned about the exploding gun yesterday. Yesterday? Yeah. You know, what if somebody, you know, I mean, okay, this guy's not making a business out of it as far as I'm aware. He's not putting his designs online as far as I'm aware. Nobody has copied this under his guidance as far as I'm aware. But what if he had? What would happen? You know, I'm pretty sure Align Technologies would sue him. If the aligners didn't work and somebody then got complications on their dental work and had to go to the dentist and get that repaired, I suspect that that wouldn't have been very good. And that person may want to sort of sue him as well, or the dentist might want to do it. Dentist might be happy, got some more business. It's not, I mean, it's just examples, and I don't see this as being a major issue necessarily, unless it starts to then explode in terms of what people are using it for. And it can be, for example, you want to set up a, okay, here's a good example. When I was at Deakin, I got an email from this guy, and he said, could you print some parts for me? And I said, well, what's the purpose of the parts? And he says, oh, they're for a medical procedure. And I says, okay, what sort of medical procedure? It turns out, in the end, this was a guy who was based in Israel, and he wanted horns on his head. And he wanted somebody to print them. So, and he had sort of approval from a surgeon to implant these horns on his, cosmetic surgeon to implant. Yeah, I know. Look at it. I see your face. I understand. Crazy, huh? But some of these people are crazy. Not when I first started getting involved in 3D printing, there was an artist. His name was, he had just one name, Stellark, Steellarc, Stellark. And he called himself a body artist. And one of the things that he did is he had a 3D printed ear surgically grafted onto his forearm. No idea why. So there are people out there that want these kinds of things, and a lot of people would then say, well, this is a bit weird and crazy. So what does that mean? What will happen there? That activity very likely may go underground. May involve people that are not particularly ethical, that don't have particularly strong medical backgrounds. And what if it was, okay, it's horns, but what if it was some kind of functional component? Maybe I wanted to be 6 inches taller or something, and wanted somebody to put length in. I mean, people do that. I mean, it is actually quite a common surgical procedure. But if you're already 6 foot tall and you want to be 7 foot tall, I don't think many people would do that for you. But so my point is, we do have to be somewhat careful about how this might affect, because it's becoming so much easier. This is a couple of students, they got the Dyson Award, which is Dyson, the vacuum cleaner guy in the UK, James Dyson, and he has an award, and these guys won it for prosthetic hand. There's a whole bunch. I've been a judge at a few awards where somebody's put forward a prosthetic hand in there, and some of them are quite accurate. Nowadays, there's even you can make these yourself with a brain interface or a voice interface, so you can actually get it with motors in there to open and close, and give signs, stuff like that. Anyway, just a point. Nelia, we done? We're done?
Yep.
Okay, we're done. All right. Boss says we're done. We're done. Okay, thank you.